Well, let's take a look here now at another one of these chain type problems. Here in example number 2. Here we have a 10-foot chain that weighs 25 pounds and hangs from a ceiling. I want to find the work done in lifting the lower end of the chain to the ceiling so it's level with the upper end. Okay, I'm going to try to draw a picture here to illustrate what it is that we're talking about. By itself, this can be a little bit cryptic. So let's suppose here that this is the picture of a room. Again, please don't be intimidated by my artwork. With enough practice, you can also be just as good. Okay, so I'm going to imagine that I have a chain here. Maybe this is like a linked chain. Okay, so I'm going to have something like this. It's very fancy. And let's suppose it hangs down like this. Now, I know immediately a couple things about this chain, and I'm going to go ahead and start by creating a number line off on the side and marking some things about this. Now, I know that the chain is 10 feet long, so for the sake of argument, let's go ahead and put, again, 0 at the top and 10 at the bottom. It doesn't matter how you label the chain. Now, I'm going to go ahead here and think about what it is that I'm interested in doing with this chain. Now, I'm interested here in taking my lower end of the chain, so down here, taking this and bringing it up to the top. That is, I'm kind of like folding the chain in half. So at the end of the day, the bottom portion of the chain that's hanging down would kind of be existing, I don't know, maybe like somewhere around here. This is where like the chain would fold in half. Now, hopefully you'd be able to determine what value on the number line would that probably be at. Well, yeah, I mean, that's probably going to be at the value of 5, right? Because if I'm folding in half, I got to be halfway in between. So here's something that's being very interesting to note here. When I think about this scenario, and I think about the fact that I'm going to be trying to move the chain, what pieces of the chain are actually going to be moved? Well, you might be able to see that it's actually only this lower half, right? The upper half of the chain doesn't need to move at all. It could actually just remain 100% stationary. It's only this bottom portion of the chain that needs to move. So I'm only going to deal with pieces of the chain in that bottom portion. Again, maybe I imagine breaking this up kind of link by link. And so what I'll do is I'll kind of say, like, again, let's look at just an individual piece of the chain here. And I don't know how long that chain is. Let's say it's delta x feet long. And let's start to see if I can find the force to move that piece, a distance that I have to move that piece, and so I can find the total amount of work required to move that single piece of chain. So for my single piece of chain here, I'll start the same way I did before. I know that the force applied to my chain, or for that piece of chain, is definitely going to be able to be found by thinking about how much the cable actually weighs per foot. Well, if this weighs 25 pounds per 10 feet, and I know that my cable is delta x feet long, again, by following the units, I can easily see here that I'm going to be left with 25 over 10 delta x pounds. That's how much that piece of cable weighs. Now, of course, I can simplify that down a little bit, right? If I divide both top and bottom by a 5, I can get 5/2 delta x pounds. But this is how much that little piece of cable weighs, so that's how much effort I'm going to have to exert on it in order to get it to move. Now I need to figure out where this piece of chain actually needs to move, and so I'll use a different color here. I know that the bottom of the chain needs to move all the way to the top, right? So like this bottom section of chain actually has to move the full 10 feet. But does this piece of chain have to move 10 feet? No, I mean, if I think about it, this piece of chain is only going to have to kind of go to like where its mirror image would exist on the other side. That's certainly not going to be the full 10 feet. So I'm going to go ahead and think about the following. Wouldn't I need to move this piece of chain kind of back to center? And then whatever that distance was that I moved, like if I had to move 3 feet back to center, to get to its mirror image on the other side, I'd have to move another 3 feet. Kind of like how down here at the bottom I have to move 5 feet to get back to center, and then another 5 feet to get to the top. So I'm going to go ahead and mark in here that there's going to be a special xi star. some representative height where my piece of chain is sitting. And so I need to move from xi star to 5, and then from 5 back to this mirror image location on the other side. So I'm going to go ahead and find that distance by stating the following. The distance that I have to move would be xi star minus 5. Notice that's the number of feet that I need to move. That's just to get back to middle. Notice it is xi star minus 5 and not the other way around, because xi star is the bigger number here on the number line. But once I've moved this distance here, I have to duplicate that distance. And so I'm going to put a times 2. So this is a little bit more of a complicated distance calculation, but once I have these, my work becomes easy. Notice again, this is work for a single piece of chain. And so I'm going to have 5 halves delta x pounds multiplied by, and I'll put the 2 out in front here, but a 2xi star minus 5 feet. For a grand total of, let's see, the 2's cancel, and I have a 5 delta x xi star minus 5 foot-pounds. So now I can go ahead and think about what's going to happen with the whole chain. So for the whole chain, I'll jump right here to my integral. I can see my function is going to be a 5, an x minus a 5, and a delta x. All right, that's what I'm going to need here. And, oops, sorry, not delta x, it should say dx. My apologies. dx. And I know that that's going to account for each piece of chain. Remember, the integral is going to say add up all the pieces and slap a limit on it as the number of pieces goes off to forever. But notice again, the bound should represent where are the pieces that need to be moved. And in this case, those pieces are only the bottom half of the cable. And that goes from 5 to 10. I'll leave it to you to go ahead and evaluate this particular integral, and it might even be beneficial to try to do this problem by measuring your blue numbers on the number line in a different order. Maybe put 10 at the top and 0 at the bottom, just to see if you can actually work through and get to the exact same answer that we ended up with here. Your integral might look slightly different, but the final result of the integral should always be the same.